So, welcome again. I would like to tell you a few things about the Kylafis lectureship. As most of us here in the University of Crete and Fourth Ecosystem know, the Kylafis lectureship was established 2 years ago in 2019 by the Institute of Astrophysics of the Foundation for Research and Technology, Hellas, Fourth, in order to honor Kylafis, currently a professor emeritus at the Department of Physics of the University of Crete, on the occasion of his 70th birthday, for his 35 years of scientific contribution and leadership towards the founding and continuous improvement of the astrophysics group at the University of Crete and Fourth. This lifelong commitment, which is actually shared by many of the first professors that established the university and Fourth, has been instrumental in the international recognition of the research activities of the Crete Astrophysics Group, which in the end led to the creation of the Institute of Astrophysics at Fourth in 2018. Under the auspices of the lectureship, a distinguished theoretical astrophysicist is invited annually at Fourth for a brief visit. Unfortunately, the president of Fourth, the chairman of the board of directors of Fourth, Lectureship Tavernarakis, could not be with us today because of a tragic event that most of us are already aware. So he sent this message that I will read to all of you. Dear Professor Silk, dear Professor Kylafis, dear Vasilis, dear colleagues and friends, I apologize that due to an unforeseen tragic event, I'm not able to be with you today on the occasion of the second Kylafis lecture. The Foundation for Research and Technology, Hellas, and its Institute of Astrophysics have established the Kylafis lecture series in order to honor Professor Nikos Kylafis for his instrumental contributions and continuing commitment towards the development of astrophysics research in Crete and in Greece. Nikos was truly a driving force behind the creation of Fourth's Institute of Astrophysics a few years ago. The process towards this ambitious objective was not at all linear, and it was through Nikos' efforts and perseverance that it eventually came to fruition. I remember vividly our long and fervent discussions about how to proceed effectively, as well as our frequent visits and petitions to the ministers and government's officials in an arduous and protracted struggle to convince about the need and indeed the added value of having a frontier research institute of astrophysics in Greece. From the very beginning, special emphasis was placed in establishing the new institute based on the same principles and terms of excellence that all Fourth institutes and activities abide to. Aiming to foster and facilitate this pursuit of excellence, Fourth has undertook several concrete initiatives, including the now long tradition of the Onassis lecture series, attracting outstanding scientists from all over the world, the intramural Fourth Synergy Grants, as well as the Fourth Research Excellence Awards, among others. The Kylafis lecture is coming as a worthy new addition in this roster of focused activities. With this opportunity, I would like to congratulate the Institute of Astrophysics and its director, Vasil, myself, for maintaining the course and organizing the second lecture despite the restrictions imposed by the COVID-19 pandemic. I would also like to thank you all for being here today to hear about the recent and exciting developments relevant to the future of cosmology by Professor Joseph Silk. I only wish I could also be with you to enjoy this presentation. Nektarios Tavernarakis, chairman of Fourth and professor at the medical school at the University of Crete. I will proceed with some information about Nick Kylafis for those who don't know him. Nick, you can see his picture on the top right when he arrived as a young faculty at the University of Crete. And the picture below is right after he became chairman of the Department of Physics a few years later. Nick grew up in mainland Greece. He obtained his PhD from the University of Patras and in physics, and his PhD in 1978 in theoretical astrophysics from the University of Illinois at Urbana-Champaign, having Don Lam and his supervisor. I think Don is among the people in the audience. Following up his PhD completion, he moved as a postdoctoral fellow at Caltech, where he worked with Peter Goldreich. And after that, he became a member at the Institute of Advanced Study at Princeton before joining the faculty of Columbia University in 1984 as an assistant professor. However, we were fortunate enough that Crete was an appealing destination for him, as well as the new physics department. So he joined the faculty back in 1985, moving through the ranks from assistant professor to associate and full professor, and retiring in 2016, becoming emeritus professor at the University of Crete. Since 2018, with the foundation of the Institute of Astrophysics, he is also affiliated faculty with us. Nick had extensive administrative contributions to the department and the University of Crete. He served as our chairman from 1999 till 2003. He then became dean at the School of Sciences and Technology, and he was also a member of the governing council of the University of Crete for 4 years. He served as the president of the Hellenic Astronomical Society, as well as the president of the Greek National Committee for Astronomy, advising the government on various issues related to astronomy. His research is in various areas of theoretical astrophysics with special interest in production and transfer of radiation, mostly in compact X-ray sources, spiral galaxies, and astrophysical masers. His early work, his most known scientific contribution is the so-called Goldreich-Kylafis effect, which is related to this maser emission. Nick, in addition to his research and admin experience, he also is an excellent teacher. He was awarded in 2019 by the University of Crete Award for Excellence in Academic Teaching. And we are very excited about that. That's why we insist that he continues to teach for free the freshman physics course every year here, and we are delighted that he does that, as well as the students. About our speaker today, we are deeply honored to have with us Professor Joseph Silk. Joseph Silk needs no introduction among the international astronomical community, but since this is a diverse crowd, I'm going to say a few words. Joseph grew up in England, and he obtained his bachelor's in mathematics from the University of Cambridge before moving to the US, where he completed his PhD at Harvard in 1968. After a brief stay at Princeton, Professor Silk joined the faculty at the University of California, Berkeley, where he stayed for almost 30 years and also served there as a chairman for a number of years. Then in 1999, he moved back to the UK at Oxford University, where he became the chair of the Savilian Professor of Astronomy, which is one of the historic professorships at the University of Oxford, which has been established, if I'm not mistaken, I saw that in the Wikipedia, back in 1619. In 2010, he became also a Homewood professor at the Johns Hopkins University in the US. And when he became emeritus professor at Oxford University, he decided to move back to the old Europe and the continent, becoming a professor at the Institute of Astrophysics in Paris and Sorbonne University. And actually, this is maybe a connection going back from Oxford to France, because reading about the history of Oxford University, it seems that some monks who had French connections established the University of Oxford back in the early 1100s. Professor Silk has received numerous awards and honors. I'm just listing a few. He received the gold medal from the Royal Astronomical Society, the Balzan Prize for his works in the early universe, the Henry Norris Russell Lectureship from the American Astronomical Society, the highly prestigious Gruber Prize in Cosmology, together with Nicholas Kaiser, for their seminal contributions to the theory of cosmological structure, formation, and probes of dark matter. He is fellow of the American Physical Society, the Royal Society, the American Astronomical Society, as well as the American Academy of Arts and Sciences and the U.S. National Academy of Science. He has many seminal contributions to a wide range of topics in cosmology and theoretical astrophysics. He is probably the most, if not among the most prolific authors in astrophysics today, having published more than 1,000 highly cited refereed papers. Several of his works are seminal and widely used. Most graduate students who study cosmology should be aware of the now famous silk damping effect, which is responsible for the structure we see in the cosmic microwave background emission. So today we are honored that we have him as a 2020 Kylafis lecturer. We wish he was with us today, last year in person. We couldn't do it during the pandemic. We postponed it for this year, but even this year it was not possible. So we decided with his agreement to have this lecture online. And we hope that he will be able to visit us in person sometime in the near future when conditions are better. And without further ado, I will stop my sharing and I will let Professor Silk take the virtual stand.
So, good afternoon, everybody. Thank you so much for that introduction. It's a great pleasure for me to give this lecture in honor of Nick Kylafis. I've known him for many, many years. We've never actually worked together, but we've had numerous discussions from his Princeton days and even before. So it's a real pleasure for me to do this. I'm going to take you on a very futuristic tour of cosmology and even more generally through astronomy in talking about the major challenges that we have and how we might hope to overcome them. So the bottom line of what I'm going to tell you about is that I think going back to the moon, which is well on the cards now, major space agencies are rapidly industrially exploring this. Industrially maybe is a word with a double meaning here, but in any case, why is it so good for astronomy? Well, it offers a space-like environment. There's no atmosphere or ionosphere on the moon. It's seismologically stable. So it's a great place to build telescopes. And what can we do with such telescopes? Well, we can develop radio astronomy at lower frequencies than we can effectively do from the Earth. We can move into the far infrared with no worry about atmospheric obscuration. We can do optical astronomy at incredible resolution and even gravity wave astronomy. I will tell you about all of these. And the bottom line really is that I think the future of cosmology, and maybe even the future of astronomy, will be with telescopes on the moon. So let me begin the story in cosmology with a founding father, really the first physical cosmologist, Georges Lemaitre, who was co-founder of course, the expanding universe model with Alexander Friedman. And here are some sketches from Lemaitre's early notebook. At the time he was visiting Pasadena and learning something about the galaxies, he had models in which the universe began from what we now call the Big Bang, a point-like singularity. And as time went on, to the right, you can see there was a period of initially in many of the models deceleration, and then many of them ended up with acceleration. Well, these are all different possible models. And we now, of course, have a modern understanding of what is behind this. The deceleration is caused by matter that we can't see, mostly by dark matter. But what is remarkable is that the acceleration, which is a mystery still, of course, but Lemaitre knew what the actual, if you like, physical phenomenon behind that was, namely Einstein's cosmological constant. And Lemaitre was very much aware, this was at the time of the birth of quantum mechanics. And in 1933, he wrote this remarkable paper in which he said that the cosmological constant could be interpreted as vacuum energy, and it would have a negative pressure. You can see his famous equation of state P equals minus rho c squared, and that's exactly equivalent to a constant. And this is what we now, of course, call dark energy. But he was very much aware that this was a property of vacuum fluctuations. So this was really tremendous foresight. So let me fast forward half a century, and the major development in cosmology was the birth of the inflation theories, some 50 years, half a century after Lemaitre's pioneering work. And these are remarkable in the sense that they take us from essentially nothing with a very early phase transition to the huge universe that we see now, and can explain a number of its properties, such as is well known, how big the universe is and how space is nearly Euclidean, much as a wrinkled balloon rapidly expanding flattens out, and so on. And even the quantum fluctuations are stretched out, as we'll see, to account for the origins of structure formation by gravitational stability in the later universe. There are issues that we have, though, if we'd like to actually verify inflation. One of them is that it does require matter that we don't see, dark matter. It does require also, to explain the late time acceleration, something akin to Einstein's cosmological constant, which can be thought of as energy fluctuations in the vacuum and negative pressure. We call that dark energy in modern parlance. And we have no evidence that these exist, the dark matter exists, and no understanding of the origin of the dark energy, other than it's simply an integration constant in Einstein's equations. However, there are very specific tests that we are in the process of addressing that in principle can be beautiful probes of inflation. So one is that there is a gravity wave background produced as inflation ends, greatly stretched out by inflation, to give you frequencies that we can in principle see today via their distortions of microwave background fluctuations. So they produce shearing modes that stretch out the fluctuations that can be seen in polarization. So the search is on for these. Those fluctuations also account for galaxy formation, and there are tests of that too underway to see if in the situation the universe is described by dark matter, which is intrinsically cold, there should be energetic traces of that as the universe developed. I'll explain that in a moment a little more carefully. Each of these has difficulties. I'll explain those two in a second. But there's one other, a third beautiful probe of the beginning, which I will argue is really the ultimate probe. And this is that the inflation theory also imprints correlations on the fluctuations, higher order correlations. And these can be seen as tiny twists and wiggles, in principle, non-Gaussianity in the microwave background, indeed in galaxy fields and matter distributions. And so that there we have several different options for trying to better understand our beginnings. So let me now take you through the prospects with the telescopes that we're building now and experiments that we're undertaking now for developing these probes further. So let me begin with dark matter. So here, it's a little bit disconcerting at first sight because we know observationally that if Einstein's theory is right, dark matter is everywhere. It most likely consists of some form of weakly interacting particle. And we can explore these particles because they would have some interactions, even very weak, with matter. And so the problem, though, is the parameter space that we could need to look in, if we're to really sample all possibilities for these particles, which we have not seen yet, but we are fairly certain they're the dark matter culprit, involve a huge span in unknown cross-section for particle interactions and unknown particle mass. And you can see on this graph, there are just many, many decades of uncertainty there that we'd like to probe. So what we can do is use other evidence to try to motivate these searches better and try to restrict the parameter space, to look for the most favored regions, let's say, of parameter space. So here we are. This red loop indicates some fairly motivated regions of parameter space that come in the upper part from arguments to do with theories of like supersymmetry and in other cases, lighter particles from QCD arguments. But so this at least tells us where we should put our efforts into looking mostly. We've done extensive searches and you can see a very brief overview of those searches, looking for dark matter evidence via its interactions. So one is it would occasionally scatter off detectors in deep underground instruments that we're building. We've seen nothing yet. It could be produced as missing energy events at high energy accelerators. We've not seen those either. And the dark matter reached its current, settled down in its current abundance in the present universe, initially by undergoing some annihilations. It was produced and annihilated very freely at the very beginning, and there should be a relic density which should still very, very weakly annihilate today, giving you gamma rays. And if you look in regions where there's intense dark matter, we haven't seen those either. So it's a little bit discouraging. No evidence yet for dark matter, but we have decades ahead of us of intensing searching to try to close up the remaining parameter space and zero in on where the candidates might lie. But so far, it doesn't look great. But the bottom line is that we just need to look everywhere that we can for dark matter candidates. So I should say that, by the way, that this includes primordial black holes as one of the candidates that's popular now. But again, no evidence for those either, for that matter, but they would be a possible candidate. So now let me turn to the second major requirement, if you like, or prediction of inflation, which is that there is acceleration, there is dark energy. And it so happens that this is important in the present universe today. And so let me just show you where we are with this. First of all, it's just a constant in Einstein's equations, but it's incredibly small because it's just being important today to explain, to account for the observed acceleration of the universe. And it's a beautiful explanation of the observed acceleration. You put in the constant, and lo and behold, when you do experiments that involve both galaxy surveys and microwave background, you zero in on If you like Lemaitre's equation of state for the dark energy, remember that was P equals minus rho c squared. And in the 20 years or so that we've been doing modern experiments, you can see that we have greatly reduced the error bars, but we're very, very close, as always, to the cosmical constant. If W were not -1, that would point to new physics, would help us understand where the constant came from that gives the acceleration. We found evidence of that. And so the question is, of course, how hard, do we go on looking? We must go on looking. We will go on looking, but at some point, we're reaching diminishing returns, I suppose, if there are no indications of deviations. And so it's a great experimental field, but it's hard to predict the future. Now, you could argue that maybe gravity is the culprit and that we should simply change gravity, and this would probably kill two birds with one stone. It would, it could take care of the dark matter for us, and it could also take care of the cosmic constant. It would be a way of better understanding what happens at the very beginning in the quantum region of the universe. So we have where Einstein's theory simply breaks down at the very beginning. And on the larger scales, we have this possible question about what the meaning of the acceleration of the dark energy is. So the alternatives are great. It's wonderful new physics. Many are being explored, but I find the motivation is weak in the sense that the anomalies with Einstein's gravity are highly debatable, and we have many, many proofs. And the theories are themselves rather ugly. So in this vast domain I show you here, which plots size of any scale of the universe versus the mass, any relevant mass, you could see that the yellowish region shows where we've probed and essentially tested Einstein's gravity. But there are vast regions elsewhere where we really could have some non-standard gravity, except that, as I say, the motivation for many of us is not as strong as it could be, but we have to look. But anyway, this also, I think, is an area where we don't see any immediate return guaranteed experimentally. It's somewhere where we have to look, and with luck, we may find something someday, but when, one cannot really say. So enough about modified gravity. Let me turn now to the major revolution in cosmology in terms of understanding precision cosmology, which has come from the cosmic microwave background. And this is now really the leader in giving us the highest precision measurements of cosmological parameters. Basically, for measuring these fluctuations, you can see here the beautiful Planck map of sub-millikelvin fluctuations in the microwave background. The sensitivity goes down to a few microkelvin. We have to do better if we're really going to look for one of the tests or the probes of the inflation theory. And our current goal, our current dream, is to measure this shearing mode produced by gravity waves from inflation in the microwave background. To get there, we need to have 1,000 times improvement in sensitivity that we have now. And that will be coming along with space experiments, not great improvements with the light burden in something like 7 years' time. And on the same time scale, microwave background terrestrial experiments at the South Pole will be exploring with a major sensitivity. And one of the major aims of these experiments will be to look for this highly elusive gravity wave signal. And the idea is to measure this shearing component, the ratio to the scalars that make the galaxies, the fluctuations that make the galaxies, to get limits of maybe 1 parts in 1,000. And that is well in the range of model expectations. The only problem is that the models themselves have huge uncertainty, and it could be that our lack of understanding of the beginning of inflation means that these gravity waves are totally too small to be ever detectable. So there's no guarantee of a primordial signal. So this leaves us wondering, where should we really focusing on our next efforts in cosmology? So I'd like to argue in the next part of this talk that there's one region of cosmology which is very much unprobed, where we can, in principle, get incredible precision. We can basically beat the microwave background by enormous factors. So the microwave background, has something like 1 million pixels on the sky, a few million pixels on the sky, and then it's limited by photon damping effects. And so that limits the information you get. We say there are maybe 1 million modes in the microwave background. And so your information is basically 0.1%. That's the best you could ever do. If you can explore the galaxy distribution, there we now have surveys which will be giving us hundreds of millions or even billions of galaxies in the not so distant future. One can use those to greatly increase the information content. But even that may not be enough. If you really want to get to grips with the fundamental inflation predictions, I'll explain what they are in a second, you have to go to something else. And there's one area of totally unexplored territory which gives me a huge boost in information content. And these are the first clouds, because there are typically 1 million clouds per galaxy, the building blocks of galaxies, hydrogen clouds. And these are present very early on, before the first stars. And these were in the dark ages. So if I can explore the dark ages, then I would have immense precision to go further and do something that I could never do in any other way. And so how would you do this? Well, the idea is you would see the hydrogen clouds and their fluctuations that produce the clouds in shadow against the microwave background. They would, because the gas is on a different adiabat from the radiation post recombination. It's cooling a little more effectively than radiation. It's colder. And so we can see an absorption, and this can be done before the first stars form, must be done before the first stars and black holes, because their radiation would then basically mess up this simple coupling of hydrogen gas spin temperature using 21 centimeters against the microwave background. And so you can see by going back to redshift, and it's something like 50, okay, that we have to get to. You can see the dip in the temperature from the adiabatic cooling of the gas. When stars form, the gas gets complicated couplings. I don't want to go into those, but we're talking about effective tens of millikelvin. Now, this is at such a low frequency. We're discussing 21 centimeters at redshift 50, that's 10-meter wavelength, that you can't really do it from the Earth. It's a mess with the ionosphere. And if we're going to explore the dark ages, and this will be the next frontier in cosmology, I think, we'd better go elsewhere. And I want to argue for you now that this going elsewhere means the moon. So why the moon? Well, the far side of the moon, it gets complicated, is the most radio quiet environment in the inner solar system. So you're shielded from the Earth, you're shielded from, cell phones and marine radar and all the noisy stuff that we do. There is no ionosphere to mess you up at low frequencies. The only problem is you have to look at a wavelength stretched out 21 centimeter as something like 10 meters. Now, the good thing is that 10 meters, the radio astronomy there is pretty trivial. These are dipole antennae we need, and they're 10-meter scale antennae. So the surface of the moon can be pretty granular, full of rocks. That won't make a hell of a difference. But still, we have to go to the moon to do this. And what is more, we need a pretty large scale system on the moon. It's no good having just one or two antennae. Fine, that'd be good for some global signal from the whole sky, as is being attempted at somewhat higher frequencies from the Earth, which is EDGE's experiment, the Australian desert. But we need to do this on the moon, and we need hundreds of kilometers of baseline to pick up the resolution that would give us all this information with these smaller structures. And to get that, we need hundreds of kilometers, and we need millions of antennae to give us the sensitivity to fill up these baselines, to dig deep into the foregrounds. And so that is the dream. This is a cartoon in which a lunar rover has laid out printed antennae on mylar strips. There are modern versions of this that are starting off with 100 antennae that are already being designed now, being built, in fact, in preparation for future lunar landings on the far side. So we're doing pilot experiments already. We have some way to go to develop the ultimate experiment. But there is one huge problem in this, and that is the foregrounds. So it turns out the foregrounds are thousands of degrees Kelvin, just from radio galaxies, basically. And we're looking for a 10 milli-K signal. So what do? Well, I think what you have to do is the classic approach that we do in radio astronomy, which is you use both interferometers and single dish telescopes. Use single dish to look for the point sources, and then you can catalog those and then subtract them out. So there is a proposal recently funded for a big major design study by NASA to go to the far side and build a huge telescope in a lunar crater. And this would do direct imaging at 30 megahertz. And it's a Arecibo type experiment. You would suspend the receiver from the rims of the crater. So that would be a crucial part of the future progress for dark age astronomy on the moon. Okay. So let me now summarize the science that you could get, which to my mind is the ultimate science in cosmology. So to summarize dark energy, so far we have no predictions for deviations from Lemaitre's value, as it were, and we, there's no guarantee this will ever come. We have to look, obviously. Dark matter, no detection yet. Again, we have to look, but we have no guarantee of a return. There's so much parameter space out there that it could be in that we may not get there for a very long time. Inflation, the tensor mode, the gravity wave mode, there seems to be no rigorous lower bound on that. So what do? Well, what we're going to look for then is the wiggles. Okay, so here in this cartoon on the right, you can see the stretching by inflation of fluctuations, and it incorporates in generic models these higher order correlations, which you can look for in the microwave background, in the galaxy distribution, and in the dark ages. And by far our best bet will be the dark ages, because that's where we have this immense possibility of precision. And again, I summarize in this table here what you can do with the microwave background, and ultimately with galaxy surveys, you can basically get to this non-Gaussian imprint. So I've indicated roughly what it was, but the numbers don't really matter. You can see why it's non-Gaussian. You're looking at higher order effects, in this case, in temperature fluctuations, but in the future case, maybe in the cloud distributions. And you're looking for a 1% effect, and that would it would need only something like the dark ages to get to that level. We might be lucky, maybe it'll be larger, maybe we'll see these effects in future surveys. But if we really want to do a robust test, we need trillions of modes, we need the dark ages, and we need the far side of the moon. So that is my dream for cosmology, I would say, on a time scale of 10 to 20 years from now. But in the last few minutes of my talk, I'd like you to take you somewhere else, which is to take you to imagine what we can do in astronomy. We can actually do far, far more than we can do now, and answer the most fundamental questions that we're posing. So we want to build telescopes on the moon, not just radio telescopes. We want to go to cold craters, huge craters near the poles. The South Pole is particularly well explored. It has craters that are ideal for infrared astronomy. Why? Because they're always in shadow. They're dark. The rims are high enough. The sun never gets too low or too high on the horizon. And the centers are dark, very cold, 30 Kelvin. And there's even a source of power because the rims are high enough with perpetual sunlight, and there's lots of ice even inside the craters. So it's a great place to have the resources to both construct and develop telescopes. And this just shows you evidence for the ice water that we've been finding in these craters. So let me not dwell on that, but it's something that is a major goal of future lunar exploration, to go to these craters and try to exploit some of their contents. And what I want to argue is that they are, in addition for harvesting or mining water, which is one of our goals in the future on the moon, because water is rocket fuel, basically, we can also be doing astronomy. Okay, so here's one thing you could do. This is a zoom in of resolution to see the first stars in a simulation. So for this, you need a 100 meter telescope, maybe a 300 meter telescope. We tried once a long time ago to build a 100 meter telescope on the Earth. The overwhelmingly large telescope, it could not be built actually. It would have basically fallen over. There are wind stresses, or engineering stresses, whatever. But on the low gravity of the moon, we could certainly build much bigger telescopes. And with these, we could look for the first stars in the universe and other things too, which I'll explain in a second. But we could do unprecedented cosmology from the moon. So here's one more thing we could do from the moon, sticking to cosmology for the moment. The microwave background is the best black body that we've ever measured. It's in the sky. You can see this amazing precision, 400 sigma error bars plotted on the FARAS data, but this was from 1990. We actually haven't done better in the subsequent 30 years in terms of improving this. So the limits are something like parts in 10 to the fourth, but we know that it cannot be, the CMB, the microwave background, cannot be a perfect black body. There must be deviations. And finding these deviations will be a great test of cosmology because they represent events, physics from the early universe. So where could we be going on this? Well, here is one option for the moon. It's to build a Fourier transform interferometer, which would basically compare a perfect black body with the sky. It would have a dual input interferometer. As the moon rotates around the sky, you would scan the sky and you would put this in a dark, cold lunar crater. And so is this crazy? Well, such a module of such an instrument fits well within the payload of a mission U.S.A. is planning in the late 2020s. This is a 1.5 ton payload lander on the moon. They're looking for suggestions, and why not include a 1.5 meter telescope that would do these amazing measurements. That's one of the many, many suggestions out there. Who knows if they will take that seriously, but this is one of the possible futures for cosmology and the black body spectrum and its possible deviations. The science you get from this is incredible. Let me tell you what that is. You'd, in principle, improve COBE by 100,000, and again, that was 30 years ago. So this is something we could do. What would you do with this amazing science? Well, you would be able to test with the spectrum a fundamental prediction of our model of cosmology, structure formation. So basically, if we believe that matter forms in a bottom-up way from small fluctuations to large fluctuations, and these are basically constrained, they're basically, it's dark matter that controls all of this. And so we have baryon clouds, if you like, inside dark matter clumps, and that aggregate to larger and larger structures. Eventually, the galaxies today, well, the theory predicts there were small structures that formed before the big ones, and they merged together eventually. And these small structures long ago, in the first tens of thousands of years of the universe, would have been damped out by friction with the radiation. And that has to leave a signal that will be seen as a distortion. And so this is maybe the most fundamental test of cold dark matter cosmology, of the bottom-up picture structure formation. You could do other amazing things too. Maybe, to me, even more amazing will be measuring the recombination of hydrogen and helium from the early universe. I mean, recombination lines are the bread and butter of modern astronomy. That's much of what we do in every part of the Milky Way and all distant galaxies, right? But imagine seeing the cosmic signal. The universe must have recombined. It certainly had helium from the first minutes. We could see the recombination lines in principle if we have enough spectral sensitivity, and that one could get with a big enough improvement, even just a factor of 1,000 improvement, perhaps, over over Phi-RAS, perhaps 10,000. And finally, if there were exotic energy inputs, you could see those. Who knows from what, black hole evaporation, dark matter, whatever. This just shows you over here where we are with where Phi-RAS was, and the enormous problem we have with foregrounds. That's this shaded gray area, and the possible signals. And you can see these wiggles here, which are the recombination line prediction, and you would get and these are in quadrature, are some of the distortions from galaxy formation. All of this is well within the range of a future experiment from the moon, possibly in space, but we're going to the moon, as I'll explain in a second, so that seems as good a place as any to do this. One final example is cosmology with gravity waves. So the moon is a gravity wave detector par excellence. So it's a bar. Think of it as a giant bar. Well, there are essentially no lunar quakes. Occasionally there's a little bit of tidal redistribution, or an asteroid may hit or something. But basically, it's seismically incredibly quiet. Many thousands of times quieter than the Earth. It's a great place to basically put seismometers. We're doing that, from the Apollo days, so we know how to do that. And with modern seismometers, one could actually have stations on the moon. There'll be a wonderful gravity wave detector. And the beauty of using the moon is that here is the sensitivity of future gravity wave experiments, ranging from the lowest frequencies, pulsar timing array, to LISA, our future space interferometer, triangle of detectors in 2034, to the LIGO Virgo detectors running today, with sensitivity curves indicated, and some of the source detections in color here. And the lunar experiment would basically bridge the gap. It would give you a wonderful way of studying the in-spiral of merging objects, and let you understand much better the role of black holes forming and modifying structure formation. So possibly, or essentially, it would be, again, an amazing contribution to our potential knowledge of black holes and their mergers and the mass distribution they could have. So let me try to put things together for you. So with lunar telescopes, the space agencies have not so far indicated huge amounts of interest. There are pilot projects, but what is getting lots of interest is, of course, the planning for a lunar space station, a lunar village. The infrastructure should be in place by 2030. Both it's being led by the US and by China. Russia's playing a role, Europe is playing a role. Much of it is driven by commercial interests. There's a huge interest in tourism, rocket fuel, I mentioned already, mining of rare elements. We're running out on the Earth over the next few thousands of years. The moon will offer a great capacity for those because of its continual bombardment by the asteroids and resupply of rare elements. So we're discussing long timescales, but my argument is that we should be thinking of building telescopes. Now, obviously, it will take us, we'll need lunar infrastructure, right? So that's, time, 10 years, 15, 20 years to build up all of that in place. But remember that big projects in science have really long lead times. So if we're going to have a 100 TV particle collider, we're discussing 2050 for that, right? Design 20 years, construction 20 years, whatever. So doing something on the moon, I think, is well within, should be well within our astronomical horizon. The cosmology is unparalleled, in my opinion. We can't achieve this on the Earth. I've tried to argue that. We could maybe do some of this in space, but the budget simply isn't there to do it as independent projects in space. But I think we can piggyback on our exploration of the moon to do this on the moon. That is the essential argument. And we say the cost is absurd, but remember the space telescope, the Hubble Space Telescope, and all the subsequent launches of telescopes by the shuttle, that amounts to something like a small add-on, 5% of the total costs involved, the International Space Station, the Space Shuttle. So it did piggyback in some ways on when decisions were made to build these other structures. So I think the future is really bright. And I'm going to close by telling you that, I've been speaking so far as a cosmologist, right? But I want to open things up now and tell you that astronomy as a whole, this will be the future for astronomy too. So why do I say that? Well, here is one of the most fundamental questions that we are asking in astronomy. Are we alone in the universe? So to understand this question, we basically need to look in detail at the spectra of targets, which are plausible targets for life. And these would be exoplanets with rocky cores, inhabitable zones around F stars or G stars. And then we would seek biological signatures. Now, in this exploration, maybe the most important thing of all are the numbers. We just need lots of examples because we have no idea what the risk factors are, what the probability factors are for reaching any level of life long before we even discuss about more advanced forms of life. The beauty of a big telescope is that it can give us many, many thousands of targets that we can follow up. LUVOIR, which is our best current hope for a space project, is targeting some 50 objects in the nearby less than 100 parsecs from us. If we were to go to a 100, 300 meter class telescope eventually on the moon, we could suddenly look at many thousands of targets. And it was seen to me that would be the only way to overcome some of the depressingly small estimates of the probabilities of life elsewhere and the risk factors involved too. So that's a 100 meter class telescope, but we can do one thing better. And now this is getting really, really futuristic, but plans are out there, designs, let's say, very futuristic designs for huge telescopes, for hypertelescopes. So here is one of them. You can imagine going to a cold lunar crater and putting lots of mirror segments on tripods. And again, Arecibo style, you'd put your camera at the focal point on a cable. And if you could correlate the phases of all these mirror segments then you could do coherent astronomy. And in principle, there are, there are schemes that might allow you to do this using advanced types of detectors. And what would this achieve for you? Well, you'll get micro-arcsecond, a few micro-arcsecond resolution. So you could look at the nearest planetary systems with this sort of, quality of image, and wouldn't that be amazing? I mean, that after all is imaging nearby exoplanets is one of the main goals of some in the exoplanet community now, and this would be a way not of doing this on a brief interval of time with a flyby type experiment, but actually having an observatory that would study these things. So that, I think, is a wish for the future, but the more remote future, for what we will be doing eventually on the moon. Okay, so let me conclude. We have many issues now in the political environment, from Europe, from Russia, from the US, China, which are coming up now as we try to plan lunar exploration. So certainly there's going to be infrastructure there, there's going to be human exploration. There'll also be robotic exploration, and that may even be dominant, but no doubt guided by humans in place. And it seems that with all of this, all the commercial interest in this, that a very interesting byproduct should be astronomy. And I'd like to, conclude by saying that this is the time, faced with all this political pressure now by agencies to develop projects for the moon, that we should be pushing to lobby for lunar telescopes to do cosmology and astronomy in ways that we may never do from the Earth or even from space. So thank you very much for your attention. Thank you, Nick, for all you've done for astronomy in Crete and Greece and in Europe. And it's been a real pleasure to celebrate this occasion with you.
Thank you very much, Professor Silk, for this very, very interesting talk. Actually, I was, when I read the abstract of your talk, I was very interested, and I thought it was quite exciting and ambitious. And then I remembered that back in 1946, Lyman Spitzer had proposed that we should go to space to have a space telescope. And this goes well before actually NASA or the Soviet Union were able to send satellites into space. And I wonder how people must have considered his proposition way back when he wrote that paper. So it is indeed very exciting. And thank you for this very interesting presentation. Now, what I will do is that I can enable people may unmute themselves, and they may ask questions if they wish. I will read a couple from the chat. One is from Nick Tsamis, theoretical physicist here in the department, who actually says that his question is: errors in the measurement of basic cosmological parameters are, as a rule, larger than basic parameters in particle physics. Which basic cosmological parameters and at what time would you think are solid enough that any theory that does not predict them can be considered unacceptable?
Well, it's true that errors in parameters plague cosmological determinations. So we're facing this with great intensity right now, because there are discrepancies between different measurements of the Hubble constant with different techniques, and of the smoothness, the clustering strength, if you like, of structure of galaxies in the universe. And we're looking at effects which are as much as 2 or 3 or even 4 sigma. Now, my first comment is this: in particle physics, one face these problems too. Okay, so we have many 2 sigma effects that have gone away. But in particle physics, one goes to 5 sigma. And at that point, 99.9% we are willing to consider awarding Nobel Prizes, right, for discovery. We're a long way in terms of the search for new physics from that gold standard in cosmology. So I think here is one of the problems which worries me the most. So we're dealing, let's consider the Hubble constant, where there is this tension now, which has prompted many people to propose that there may be something wrong with the standard cosmology of Lemaitre et al., Lemaitre, Friedman et al. And my worry there is that we're using supernovae and Cepheid variables as distance calibrators. And this is a slightly dangerous procedure. So we have no fundamental theory of how stars explode. It's very phenomenological, and there may be systematic issues that come up when we use supernovae. They may vary in their peak magnitude from place to place, environment to environment, in ways that we don't fully understand. Cepheid variables, the other part of the distance ladder, are maybe more reliable from the point of view of basic physics, but equally as distance calibrators, we're discovering uncertainties in recent work that say there's something unknown about their use, and specifically, in the recent months, even it's turned down to be questions of the dust that surrounds both of these objects is like no other dust that we see in the Milky Way galaxy. So something slightly funny is going on. So I would conclude from all this that we're just a long way from controlling systematics in cosmology, and that is why I think the call for uncovering new physics is going to take a while until we get better control of those.
Thank you very much. I see there was a question by Professor Tsinganos, which was written in the chat, but I think he may also want to ask it because his microphone is on.
Yes. First, please let me know let me make a short note about my colleague Nick, since we arrived together in Crete back in 1986, almost 35 years ago. Nick was coming from Caltech. I was arriving to Heraklion from the Center for Astrophysics at Harvard. We share an office door, the next door. So I believe Nick has been a cornerstone for building the very impressive astrophysics group of the University of Crete. Second, let me take also the opportunity, Professor Silk, and ask you, first of all, I mean, your talk was excellent, in particular the Lunar telescope's proposal you have put forward. And I would like to ask a very basic question for most of the readers, namely, what's your explanation that the cosmological, they say the largest deviation between proposal and observation has been this famous cosmological constant, the value of the cosmological constant, the small value. What is your proposal to resolve this huge difference between the theoretical value of the cosmological constant and the proposed value of the cosmological constant, which, as I said, is the worst theoretical prediction in physics, if I can say. Thank you very much, Professor Silk.
Well, it certainly has been argued that the predicted value is 120 orders of magnitude larger than what we observe of the cosmic constant.
No.
But my view is the following, that we don't have a theory of that first instant of time. We have not yet succeeded in combining Einstein's gravity with quantum theory. So it's a very dangerous to say that there is a robust prediction. So that may well come someday. I hope it does, very much. But I think it's premature. And I would say failing that, and given that we've seen no deviation whatsoever from Lemaitre's original cosmological constant, right? This W parameter is -1 to a couple of percent as its experiments get better and better, then I would say, well, maybe it's just a constant of nature. There are other constants of nature out there that we have no fundamental explanation of. I would be happy to dial this in as an integration constant in Einstein's equations, and it's just one more constant that we maybe someday we'll get a better understanding of where it came from when we have our fundamental theory of quantum gravity, but right now we don't. So that I think is where I would stop, and I personally am not too bothered by this possible contradiction.
Okay, there are some raised hands. Dimos Kazanas from the east coast of the US actually may.
I may be, I'd like to turn on my camera here so that Joe can face his accuser here, as it is customary in the U.S. courts. Seeing your talk from far away, it seems to me that cosmology now has come to a similar situation with particle physics. Particle physics has a standard model with 26 parameters that explains essentially all experimental data. And we're searching now for phenomenology beyond the standard model. And it seems that we are in the same situation in cosmology. Namely, we have a much better model because it only has 6 parameters and explains effectively all the cosmological data to some extent. And we try to find deviations, if you like, or maybe confirmations of the model maybe it would be nice to have a telescope on the moon. But tell me, is that my view correct to some sense?
We certainly do have what most of us regard as a standard model of cosmology. And it's also true that we have not seen any strong deviations. There are hints of deviations, but they're simply not robust. And one can attribute them to systematics. And similarly, in the standard model of particle physics, it's an amazing fit to so much data, but there are, 1 or 2 things, neutrino masses is one example, that don't fit into the standard model. So we know we have to go beyond the standard model. Maybe cosmology is at that stage too, because we know to understand better the beginning of the universe, we need to go beyond the model we have now. So yeah, the theories demand more, but I don't think there's any reason yet to reject in cosmology our standard model. It fits everything we have well enough to, I think, satisfy us and enable us to make predictions for future experiments to test it better.
If I may continue, just once more, I'll quit after that. There is, for example, the issue of dark matter, but my friend Stacy Mago shows that dark matter really is associated with a characteristic acceleration. We have a dark matter only when acceleration drops below some characteristic value, which interestingly enough is of the order of CH0. The acceleration of the universe, it seems to involve the same acceleration parameters. So maybe we don't have to go to the moon to see that there are issues that are still open that has to be addressed. You showed actually in one of your first diagrams, mass versus size relation. and you show the black holes, which of course is a linear relation, of course. But if you draw a little bit more accurately the universe, galaxies, forget about the sun, even the electron or globular clusters, you find out that the mass radius relation goes like a square, like the mass goes like r square, which of course implies that if you take the m over r square, that's a constant acceleration, or a constant column density, if you like. And it's a fact that the column density of the universe is comparable to the column density of the galaxy. It's about 10 to 22. And interestingly enough, it's comparable to the column density of the electron for some strange reason. And so there may be issues that still are within the measured values without having to go to fine detail that we still have to address with the better theories, maybe.
I mean, I couldn't agree with you more in that there are hints from nature about coincidences. I mean, you know, we go back to Dirac. He was saying this a long time ago and before him even. But it's one thing to go from hints to physics. That's a different matter. And I think the trouble with, let me just generally say, Mondian type explanations of dark matter is that one can achieve similar phenomenology with standard physics, Einstein type gravity. So it's complex, obviously. You have to add, you know, messy baryonic physics, et cetera, and so you have to choose between, you know, do I say this is just a hint of something new and fundamental, and I'll be foolish not to explore that further, I entirely agree, or do I just go for developing better my framework of galaxy formation, which we're only just beginning to scratch, you know, below the surface of. We haven't yet really understood numerically how to connect star formation and galaxy formation, let alone the larger scale. So I think there's, you know, enormous strides to make there before we can begin to question the fundamental physics of nature.
Thank you very much. I'll stop here.
Okay, thank you. There is someone called Nikos who has his hand raised.
Okay, yeah, it's me, Vasilis.
Not Nikos. There are many Nikos.
I know, Hydro. So I
Hello.
enjoyed your talk once more. I have two short questions. One is on the moon. I don't know if you remember the title of a famous science fiction novel by Robert Heinlein back in 1966. The moon is a harsh mistress. It turns out that the moon environment is not so favorable to whatever kind of instruments. You know that it is this dun regolith, which minuscule dust grains, which can fix in basically, which can enter any joint and be fixed on any surface by virtue of their electrostatic static electricity. So in those conditions, the maintenance and protection of any instrument on the moon is much more difficult than on Earth, and it will require not perhaps humans, not only robots. It's not just building some instrument on the moon, it's also maintaining it, not to mention the cosmic rays that can break down a lot of electric devices. So that's the problem with the moon. I don't know how much time we will need to go beyond those obstacles. I suspect it will be more than a couple of decades. But anyway, perhaps at some point it will be done. Now, I have a second short question about cosmology and inflation. The inflationary paradigm was established 30 years ago. It's 30 years exactly since the paper of Alan Guth. I would add, since I saw my good friend Dimos there, it's 31 years since the paper of Dimos back in 1980 on something like inflation. Do you think that inflation can be now considered as a well-established paradigm of the earliest universe? I mean, for the expanding universe proposed by Friedman and Lemaitre, a few years later it was proved by Hubble's observations. And when Gamow started working with the hot early universe in the mid-40s, then 15, 20 years later, after the CMB was basically described by Alpher and Hermann it was discovered by Penzias and Wilson. So we had observations that proved that these things existed and they are with us. And now there is no risk that the hot early universe is overthrown by some other theory. It could be completed by something different, of course, but not overthrown. So do you think that now inflation, on which many predict, which has a lot of successes, of course, you know much better than I do you think that inflation is so well established as to not risk to be overthrown by something completely different? Okay, so that's my two questions.
Okay, so let me begin with dust. Of course, it's a severe problem. One slight advantage that we have in the dark craters is that the dust gets charged by the photoelectric effect in general on the surface. And so, and at night it falls down when the photoelectric charging no longer works. So that leads one to hope that in the dark craters, which are perpetually dark, there may not be very much dust in the air. Now, I imagine also that we will have to develop sophisticated ways of keeping dust off the telescopes when we build them there. But, you know, these are just technological issues. So I'm not too worried about this, actually, in the long term. So inflation, well, you know, there is a real question. It's a wonderful theory. Phenomenologically, it fits beautifully so far. But the problem is that we don't really have a very good beginning for inflation. The initial, you know, rolling down the potential well of the inflaton field that leads to inflation. One has to go to trans-Planckian energies, that sort of thing, to get something to work. So there are big questions. You know, the theory simply so far is incomplete. And I think it's, now I agree, it seems to have passed so many tests phenomenologically that it surely will be in the core of any future theory. But it would be awfully nice to have a better understanding of the physics that drives inflation. So I'm hopeful this is the major gap that will come from the future. And this is one of the goals that I think my discussion of non-Gaussianity from the beginning will help explore by restricting the options for the beginning.
Okay, thank you very much, Joe.
Thank you. We have Vicky Calogera for the Great Plains of the Midwest, and we're in Chicago. Snow has melted in Chicago, I presume, so.
Yes, yes, it's almost summer here. Well, first I want to say a couple of things about Nick Kylafis. I've known him as a mentor since I was an undergraduate student. He opened the door for me into the Erasmus program and opened up a lot of opportunities for me, so I'm really grateful. So thank you, Nick. And then Joe, it's a pleasure to see you again on Zoom, and thank you for the talk. I have a question about the the planning of potentially going to the moon and actually doing astronomy and cosmology from there. The Artemis program, actually, I don't remember, is the station discussed to be on the bright side or the dark side of the moon?
Well, it's an orbiting station, so it'll do both.
Ah, okay, all right, okay. So then the proposal would be to actually put something on the Earth where we, on the ground on the moon where we need it to be. And then the second question is, of course, the dark side for radio astronomy would be better, but do you think on the bright side it would basically be useless because of interference? Or is it necessary to be on the dark side? It's better, but is it necessary?
I suppose it all depends on the frequency range, but if you want to go to the lowest frequencies, that is, maybe 30 megahertz, then I think it better be the dark side. You could certainly do higher frequencies from the near side, and that would certainly have its own uses, but to some extent, you'll be duplicating stuff you could probably do from the Earth. So
okay, yeah, exactly.
Probably, yeah.
It wouldn't be worth it. Last quick question. would it be, was it proposed seriously for the decadal survey, the US decadal survey this time?
That's a good question. I do not know the answer, actually.
I don't know either.
I know
Okay.
that, you know, for example, Jack Burns has one experiment that will build an interferometer on the far side of the moon. But that will happen, you know, in 5 or 7 years' time. I'm not sure what that or its successors had, whether that had any mention or discussion in the decadal. So I haven't seen the results. I want to see the results.
Okay, all right, thanks.
There is a hand raised by George Kastrinakis. George? I don't see, maybe he's not there. There is a general question by Gina Panopoulou, our alumnus from here, who is a Hubble Fellow at Caltech. Gina says that a question on the politics of lunar telescopes is the idea that these large constructions on the moon are country agency based. Are we going to have a race to secure territory on the moon? Or are these plans to make this planet-wide accessible, not just controlled by ESA, NASA, or JAXA? Do you know any?
Yeah, so that's an interesting question. I think we, at this point, we have absolutely no idea. There is a space treaty that goes back, I think, to 1976 that does regulate certain things on the moon. 120 countries signed up to agree not to pollute the moon. They agreed not to have any military presence on the moon and so forth. But beyond that, I think it's very much open at the moment. Different agencies will be competing for different parts of the moon, especially near the South Pole, where there are these permanently shadowed dark craters. And I think we hopefully will have to have some international treaty in force, you know, in the next 10 years to regulate this. But so far, to my knowledge, we are some distance from figuring out exactly how this will be done.
Thank you very much. Actually, since the time is passing, I see a comment by Don Lam, who mentions that Nick was actually his first graduate student and has very many special memories from the time that he was his graduate student. I don't know if, Don, you would like to say something or not. You may, if you wish. He has done fairly well, I guess, right, Nick?
Yes, well, thank you, Vasilis. Yes, I just want to say that, Nick, I was so fortunate. I was quite young at the time, as were you, and I was so fortunate to have you as my first graduate student. I mean, you were so smart and so good a scientist, but also so good a human being. And I feel very, very lucky. We were kind of a team at the time, and so you have been someone who has added to my scientific life and to my personal life over all these years, and I'm very grateful, Nick. And I wish you all the best and very, very many more years of being able to attend these lectures in your honor.
Thank you very much, Don. Thank you, really.
And maybe at this stage, I would like to ask, since the time is passing, I would like to ask anyone who would like to open their camera to do so. And I will, since we cannot have you here in Crete physically, and then go out for dinner to one of the well-known restaurants that are offered here in Irakli, I would like to ask if you would like to open your camera if you wish, and I'll just take some pictures with you and Nick, and just wait for a few minutes. And then I would like to thank again on behalf of all of us, Joe Silk, who, hold on a second, I cannot really talk, and it's like President Ford. talk and chew gum walk and chew gum at the same time. So let's see if I. Okay, one more. I think we made it.
Hey, hello.
Very many from I see very many familiar faces. Thank you very much for joining us. It's very unfortunate that we couldn't host you.
I want to say something now that I see Jim Truran. Good to see you, Jim.
Good to see you, Nicholas.
Now,
Hi.
as Don said,
Hi, Jim.
I was his first graduate student, but there is a regulation at the University of Illinois that says that you cannot have a student, a PhD student, until, unless you've had one. So it's a catch-22. So to overcome that, Jim Truran was my de jure advisor and paid my salary, and Don was my de facto advisor and advised me on the project. So I thank them both sincerely out of my heart for their support during those years and the friendship we have had after that.
Thank you, Nikos. We love you, Nick.
Good.
Ευχαριστώ πολύ.
I would like to thank again on behalf of all of us, Professor Silk, for accepting this to be our second Kylafis lecturer and investing this time to be with us at least virtually. And we do look forward to having you here in person anytime it's convenient for you. Thank you very much. Thank you everyone for joining.
Thank you, Vasily. Bye.
Thank
Bye.
you.
Bye, everybody.
Bye, everybody.
Thank you. Thank you.
Bye.
Thank you. Goodbye.